Hi, everybody. I'm Reza Shadmer. I'm recording this on a rainy Saturday afternoon in Baltimore, Maryland. I hope you're doing well. And I hope this experiment that we're going through, this teaching using remotely, is of value to you. It's the first time for me. And so I hope it goes okay. Let's get started. So what I'm going to be teaching you about is the concept of utility and mathematically thinking about a number of questions regarding how we move. Let me explain to you those questions. So um, let's imagine two friends meeting each other. What are they going to do? Well, if they haven't seen each other for a while, they're going to run toward each other. So we can ask a simple question. Why do we run toward people we love, but only walk toward others? Now, after we meet our friend, we're going to spend some time with them. So we can ask a different question now. Once we arrive at where reward is located, what determines how long we should stay? The purpose of today's talk is to ask these questions mathematically and then ask, can we come up with some scenarios, some derivations that can help us understand our behavior? All right, let's get started. Now, to get started, I'm going to have you participate in an experiment. Here's what we're going to do. Look at that dot at the center of the screen. Now I'm going to show you a couple of images. What did you do? Well, more than likely, your brain assigned a value to the stimuli that I showed you. And it turns out faces are more valuable than patches of noise. So probably what you did is that you made a saccade toward the most valuable stimulus, which in this case was probably the face. So, okay. Now, after you made the saccade, we can look at the velocity profile of the movement you made. So here's the velocity of the saccade if you made it toward the face. Here's the velocity of the saccade if you made it toward the noise. And you notice something. The vigor by which you move, the velocity of your eye movement is higher when you are going towards something that you value more. That's the basic idea, that we run toward the people we love and then we just walk toward the others. And it's not just true in how we walk and how we run, but it's also true in how we make saccades, which makes it much simpler to study this beautiful phenomenon. Now, after you made the saccade, you were there looking at the image. Well, all right. So you made that fast saccade. But now what's interesting is that when you arrived there, you were likely to stay longer and look at the face. So you not only made a faster saccade toward the face, but after you got there, you were more likely to stay there and evaluate what it is that you're looking at to harvest that reward. Okay, so let's put this in a framework that we've been studying in the last couple of days in terms of utility of action. So we have some utility associated with our behavior, some cost, some kind of a formulation that we're trying to optimize. That determines the control policy. So the things that we're trying to do in order to maximize our utility. So we think perhaps the basal ganglia and the various cortical regions have something to do with formulating this control policy. That results in certain motor commands that act on our body that result in some state change. All right. Now, as we generate those motor commands, we make predictions about what's about to happen. We think this has something to do with the cerebellum. Then sensory feedback arrives, and then we combine what we observed with what we predicted, and that becomes our belief. So that was the notion of the Kalman filter that you have learned, something that allows us to incorporate our predictions and combine it with our measurements. We think the cerebellum has something to do with making those predictions. All right. Today, our conversation, our talk is about this, the utility of the action. What's this cost that we're trying to optimize? So what's this utility? What is it that our brain is trying to optimize? And the way I'm going to try to explain it to you, we're going to look at behavior of certain animals. And I'm going to focus on one particular experiment that comes from Alejandro Koselleck. And at the end of the presentation today, you'll see all the references. So we'll get to the specifics pretty soon. Okay, here we go. What happens? The idea is to observe the action of animals and then to attempt to understand what is the economic variable that you're trying to optimize. So here's the experiment. We have a starling. Here's our starling. And it's got a perch. It sits here. And he can walk to this perch that's nearby to get some reward, or he can fly to this faraway perch in order to get reward. Now, the key is that there is some costs associated with this behavior. And what are these costs? Well, he has to spend energy. He has to spend energy to walk. We're going to call that CW. And he has to spend energy to fly. That's CF. And it turns out that the rate of energy expenditure during walking is a lot less than the rate of energy expenditure during flying. Flying is much more energetically costly. Now, what we're going to do is we're going to present this starling a reward, let's say alpha. And there's some caloric value to this reward. We're going to give the animal the option of walking NW times or flying NF times in order to get this reward. And we're going to record what option does the animal choose. Does he like to fly 10 times rather than, walk 10 times rather than fly 3 times, in that he finds that flying is much more energetically costly, is unwilling to do it for the reward? Or what is the relationship between walking and flying and the decision-making process for the animal? Which one does the animal prefer? Okay, let's come up with some hypotheses about the utilities that are being used by this animal to guide its decisions. One utility is called the capture rate, which is basically the difference between reward and effort divided by time. So for example, the utility of walking NW times is the reward that I'm going to get at the end of my number of walks minus the number of walks times the energy, the total energy that I'm going to spend making those walks, CW, which was the rate, TW, which is the duration, divided by time, which is how long it took. That's the utility of walking NW times. What's the utility of walking NF times? Well, similarly, except we're going to replace CW with CF, which is the metabolic rate of flying. So that's one idea. All right, we could have another hypothesis. We could say that, well, really all that matters to the animal is the rate of reward, which is reward divided by time. In this case, the utility is simply the ratio of the reward at stake divided by the time it takes to get it. Now, keep in mind that the units for all of this is energy per time. So the numerator is energy. The denominator is time. So what we're comparing is energy rate. And we have 2 ideas so far. We have the capture rate, we have the gross gain, and we also have a third one. We can have efficiency. So maybe what matters to the animal is the ratio between the gain that comes at the end of this movement, the reward, to the energy spent to make the movement. So this would be for walking, the reward that comes at the end of the walk, the ratio of that to the total amount of time, total amount of energy it took to make that number of walks. So number of walks times the rate of energy expenditure times the total time. So each of these hypotheses gives us an important indication about what the utility might be. But how do we test which utility is the one that the animal is using to make its decisions? So here's how we do it. So let's look at the capture rate. Say that's the hypothesis that we want to test. So let's plot the utility of walking. So there's some reward at stake, alpha, and you can plot this function, which is the capture rate. Its units are joules per second, as a function of number of actions that are required. So if I have to walk 30 times to get your reward, my capture rate is about 9 joules per second. Whereas if I have to walk 10 times, my capture rate is about 20 joules per second. All right, so that gives us a quantitative measure. What if you ask me to fly? What if the starling has to fly? Well, flying costs more than walking. So you see that the function falls faster. So now the cost of flying 10 times in terms of utility is about 9 joules per second. Okay, so now what we do is we say, let's pick a certain number of flights that the animal has to do. Suppose that we give the animal the option of flying 6 times. So the animal has to fly 6 times. This is the utility for it. Well, how does that compare to the utility of walking? There it is. That's the same utility. And then we come down here and we see that's 15 times walking. So 6 times flying is equivalent to 15 times walking in terms of this utility. And we can do the same for each of the other utilities that we talked about. So what we're doing is measuring indifference. When utilities of 2 forms of action, walking and flying, are equal. And then we ask, okay, how many walks is equal in terms of utility to a given number of flights, which is this condition, utility of one form of action being equal to utility of another form of action. All right, so now Koselleck does the actual experiment. He goes and he gives the starlings the opportunity to choose. What would they rather do? Walk a certain number of times or fly a certain number of times? And he measures what are called indifference curves, which are how many walks are equal to a given number of flying trips. And let me show you what he finds. So this is the curve that comes from the efficiency hypothesis, and that was reward divided by energetic cost. This is the curve that comes from reward rate, which was the gross rate, which is just reward divided by time. This is the curve that comes from the capture rate, which is reward minus effort divided by time. And what do the starlings do? They follow reasonably closely the capture rate. So the capture rate is currently our best candidate for utility function, which is the difference from reward that you got minus the energy that you spent divided by total time that you were involved in the process of acquiring that reward. So this is what we're going to focus on now. Okay, so this is our utility. Reward minus effort divided by time. Here we have it. Reward minus effort divided by how long it took to do it. Okay, so now let's consider some issues with this formulation of utility. The first one is, well, reward isn't really acquired immediately when our action ends. Rather, we harvest the reward gradually once we arrive at our destination. So, for example, say you're meeting your friend. If you're walking to meet your friend, then you harvest the reward of being with them over the time that you have to spend with them. You gradually acquire. When you go to a restaurant, you spend time eating the food. You're harvesting the reward. So it takes time to harvest reward. And of course, it takes also energy to harvest reward. The second thing that we have here is this effort function. It depends on duration of your movement. It depends on how you're moving. So basically, if you run, you arrive at your reward site earlier, but need to spend greater amount of energy. So let's first build our reward function that reflects more accurately what it means to harvest, and then build our effort function so that we can more accurately describe vigor, which is how fast we're moving. And then once we have it, we will optimize our actions. Okay, let's begin with the harvest function. And here's the idea. It takes time and effort to harvest reward. So a typical harvest function might look like this. So there's some amount of reward available. This is the total amount of reward available at the site where we're going, and it takes us some amount of time to harvest it. And this is the shape of the harvest function. So it looks something like this. The longer we are there at the harvest site, the more reward we're going to be able to harvest. But we're going to have to spend energy while we're there. So we don't get reward for nothing while we are spending time at the harvest site. So maybe this is some effort function. In this case, it's linear, let's say. So the sum of these two gives us a harvest function, which tells you that there's some optimum time associated with leaving your harvest. This is the maximum energy you're going to get. Beyond that, the amount of effort that you're spending to get reward is not actually helpful to you. So the harvest function describes the mechanisms by which the reward is actually acquired at the harvest site. All right, what about the energy that it takes to actually move to the harvest site? You know, with the energy that it takes to walk, to fly, and so forth, to get to the location where the reward is located. Let me show it to you for walking. So this is the energetic cost of walking in humans. So what you see on the y-axis is the average rate of energy consumption, On the x-axis, it happens to be the average squared velocity of the walking. So this simple relationship tells us that the rate of energy expenditure for walking is a linear function of the squared average velocity. So what this means is that we can compute the total energy expenditure associated with walking. So if you're walking a duration tm, a distance d, what you have is a linear increase plus a hyperbolic decrease. So what we have is the sum of these two functions. That's the integral of this. So if we now plot this energetic cost of walking as a function of distance and duration of our walk, we get something rather beautiful. This is the energetic cost of walking 50 meters as a function of duration of walk. So what you see is that there's a minimum. So there is an optimum speed by which to move between two directions if all that mattered to you was minimizing energy. So people in biomechanics, for example, study these functions because they want to know what's the best way to move between two locations for an animal. And that best way, if all that mattered was energy consumption, is the minimum of this function. But however, our objective isn't to minimize energy, it is to maximize utility. And what does that mean? Well, here's the utility associated with our behavior. We have some locations where we move to, where we have some reward alpha. We're going to spend some time, TH there, that's the harvest duration. And in order to actually move to that location, we have to spend energy. We have to walk, we have to run, we have to fly. And there's some distance D, and there's some movement period associated with it, TM. And the division is made to this denominator, which is the sum of the time we're going to spend. So this is the average rate of energy, which is basically the capture rate. Reward minus effort divided by time. So the idea is that animals decide on what to do based on the energetic gain associated with the option, this, minus the energetic loss associated with acquiring that option, this, divided by the total time it takes to travel and harvest that option. That's the denominator. And that's the basic idea behind an important theory in ecology called optimal foraging theory. Optimal foraging theory suggests that the decision-making of animals regarding how far to travel for the food, what to eat when they arrive, and how long to stay is based on an attempt to maximize the global capture rate. So do you see the link now to the idea of why do we run and how long do we stay? You see that it takes energy to run to where you want to go, and you could have spent less energy if you walked. And then once you get there, you have to determine how long you're going to stay, and that's the harvest function. And so we're going to use this theory now to understand control of decision-making and vigor. And that's the basis for the rest of our presentation. So how do we do that? What's the optimum behavior? And the first question is, well, what reward site should I choose to explore? The second question is, how fast should I travel to the reward site? And the third question is, how long should I stay and harvest reward? So what reward site? That's when you made a saccade. You made a saccade toward the face. You decided that was a better choice than the noise. The second question was, well, how should I make that saccade? How vigorous should that saccade be? That's the second decision that the brain made, and it made the movement. After you made the saccade, you stayed there for a while and you harvested the information that was there from the face image. So how does these processes take place? The answer comes from marginal value theorem. This is a method that is provided to optimize the global capture rate. So here's our function. This is what we're trying to do. Optimize this U bar, which is the global capture rate. So suppose we've chosen a reward site N to explore. We have two unknowns. We want to know how fast should we move toward that site, TM star. And we have to know, well, after we get there, how long should we stay, TH star. And the simplifying assumption that's made in marginal value theorem that our behavior at location N has no effect on rewards or efforts that come later. The idea is that when you get to the location N where the reward is, it doesn't affect the availability of rewards and efforts that come afterwards, which is represented mathematically this way, that you can take this sum and say your behavior at location N has nothing to do with things that came before and after. So everything else in the sum becomes A and B in our equation. Okay, that's marginal value theorem based on that assumption. So now what we're going to do is that we're going to say what's the best TH and what's the best TM that you could do to maximize U bar. And the way you do it is calculus. You'd find the derivative with respect to these, and there's something beautiful that comes out of that derivative. And it looks like this. It says that the optimum behavior is defined by these two equalities. The first equality is a description of how fast to move, which is saying the rate of energetic consumption should be such that it's equal to the negative of the global capture rate. How fast to move, the answer comes from the rate of energetic loss. The rate of energetic loss during movement should be equal to the negative of the global capture rate. How long should you stay, which is the answer to the second equation. And the answer is the rate of energetic gain during harvesting should be equal to the global capture rate. I'm going to spend a little bit of time on this so you can get an intuition about what this equation is saying. Okay, this is the energetic cost of, say, walking. So you see a concave upward function. Now, you might think that the best way to walk is to be at the minimum, but that's not what this equation is saying. This equation is saying that you should walk in such a way that the slope of your energetic loss is equal to the negative of your global capture rate, and which is, in this case here, it's not zero, it's someplace else. And it's saying, the second equation, it's saying that you should stay and harvest reward, not until this equation is maximized, but until the slope of the harvest function, this is a harvest function, is equal to the slope, to the global capture rate, U bar. So U bar is this average energetic gain that you've been getting. It's like the average reward rate. And the idea is compare what you're getting locally or spending. So, sorry, compare what you're getting or spending with the average that you've been acquiring. That's this average, U bar. Use your history as a guide to compare with the current rate of return. And that's the solution that comes from marginal value theorem. Okay, so let's show you some predictions of this theory. For example, let's look at harvest duration. How long should you stay at a place where there is a reward? Well, if there's high reward, then the harvest function rises up higher. If there's low reward, it's lower. But you notice that the place where the slope is equal to U bar implies that you should stay longer at harvest sites that have more reward. So here it is. The harvest duration is longer if there is more reward because the slope matches U bar later. Okay, what if there's effort involved in acquiring that reward? Well, if there's effort involved, then the function is going to be saturated. It's going to be suppressed downward. And this naturally says you should leave earlier harvest sites that require more effort. Most interesting is the effect of history, which is basically how things have developed for you until you get to this particular reward site. And if your reward history is high, then the slope is large. And it says you should abandon the reward site sooner. What does that mean? That means that you're living in an environment that is rich, that the value of time is high. And so therefore, the cost of time should force you to leave earlier, despite the fact that this reward is continuing to increase. On the other hand, if you live in an environment where your reward history is low, given a particular harvest function, you will stay longer. So if the long-term capture rate is low, you should stay longer at a particular harvest site. What about vigor, which was the velocity by which we move? So remember, that comes from the effort function, which is the energy that you have to spend to get to the reward site. And basically, it's a similar idea, right? That the energy that you spend is going to be optimized if you match it to the average capture rate, the U bar. If you happen to be acquiring high reward, then you should move fast toward it. If you've experienced high reward, your past U bar is high, you should move faster to the next site. And this is really an important idea. It says you not only should move faster toward things that you value more, after you've had a good harvest, you should walk away faster. It's like the old concept of after a great meeting, they left with a spring in their step. Why? Because the reward rate is high, which means that the slope is high, which means they should walk faster. They should have a shorter duration. And after expending high effort, move slower toward the next site. Okay, so these are just some mathematical ideas. Now, we want to ask the question, how do we test these predictions? Is there a simple way to go after it? And remember, we thought that eye movements are a reasonable proxy for these kinds of vigor and harvest types of movements. So let's look at that. So here's what we're going to do. We're going to have a person look at an image, and they can stay here as long as they want. And when they're ready, they make a saccade to the next point. And this point here, they don't know what the value of this point is. They make a saccade there. Here it is. And once they get there, you see an image as well. And they can stay here as long as they want, and then they make a saccade elsewhere. So first of all, you notice some images are more valuable than other images. Second, you notice that this is the midline, and so if you hold your eye here, it takes a little bit of effort. But if you hold your eye here, which is far from the midline, it takes a great deal of effort. So we can manipulate effort as well as reward associated with that harvest. And so you make a saccade and you see another image there. So let's look at some of the predictions and the results of this theory. So first of all, the obvious thing is, if you're looking at something, that something, the current image, the more valuable it is, the longer you stay. So here it is, a face image, you stay longer at the face than it would these other images. So we stay longer at a more rewarding site. People linger longer, looking for a longer period of time at the images that they value more. But what if now look at the velocity as they leave that image? So remember what the theory said. The theory said that if the past image was rewarding, then what you should do is that you should abandon the next image sooner. The harvest duration on the next image should be left earlier. So the effect of past reward on gaze duration. And we see that following high rate of reward, we stay a shorter amount of time at the next site. Next, what we can do is look at the effect of effort. So what we see is that if harvest requires high effort, we abandon the harvest earlier. So if it's hard to harvest that effort, we're not going to stay as long. And next question is with regard to the vigor of my movements. And it turns out that if we expect high effort at the next reward site, we move slower toward it. All of this is consistent with the theory that I was showing you. But there's one interesting aspect of behavior that is inconsistent, and it comes here. It says that following a high rate of effort, if we have spent effort acquiring something, we move faster toward the next site. So it's curious that expenditure of effort seems to increase our value for the thing that we've been spending effort toward. Okay, so we began with a simple question. We tend to move faster toward things we value. Why? And we introduced the concept of a utility. We said the global capture rate is a reasonable proxy for utility of action. We spend energy to move, but acquire energy through reward at the site where we arrive. Moving faster requires more energy, but this is justified if our objective is to maximize the global capture rate. That's what we got from the marginal value theorem. Now, the results that I've been showing you are from the papers that you see here. And if you're interested in learning more about it, there's a forthcoming book that describes much of what I've been describing for you in today's lecture. All right, let's summarize our story. How we move appears to be a reflection of our reward and effort history, our capture rate. So if you're feeling depressed, if your reward rate is low, you don't have to tell me how you're feeling because I can see it in how you move. It affects your movements. And the reason why, as we see mathematically, potentially is because of the relationship between the capture rate and the way optimum behavior should be done. Now, control of movements and control of decisions appear to be linked because both contribute to the global capture rate. It's not just deciding how long to stay or which stimulus to choose, but also how much energy to spend to move toward that stimulus. And so therefore, I think it's not surprising that neural systems that control how we make decisions, for example, neurotransmitters, dopamine and serotonin, things that are affected in diseases like depression, like Parkinson's disease, they not only affect decision-making, but they also affect our movements. Thus, diseases that affect one form of behavior also affect the other. Okay, I've come to the end of my presentation. I'm going to end with a poem for you, which I think it nicely encapsulates much of what I've been saying. This is from Hafez. Hafez is a 14th century Persian poet. He says, "Because of our wisdom, we will travel far for love, as all movement is a sign of thirst, and speaking really says, I'm hungry to know you." Thank you so much for your time, and I hope to see you in person someday. Take care of yourself.